Okay, so here's where we were last time. We were talking about line integrals. What I'm momentarily referring to as just line integrals. So a quick reminder, the idea is we have a domain that is dimensionally awkward, right? So it's in this case a one-dimensional thing that does not live in a one-dimensional world. It lives in let's say a two-dimensional world or a three-dimensional world, like I have two-dimensional drawn here. The idea, though, is that it's still perfectly plausible that we might want to compute the mass of such a thing or the number of ants crawling on such a thing, and therefore need to do a chop-it-up, add-it-up strategy, focus our attention on one little piece at a time. On each little piece, we can describe what's going on that piece. A little bit of calculus that we talked about last time. I won't go through the details again. And the punchline is this length, ds, can be rewritten through a pullback as this. It's speed times dt. Notice then the result is after you pull back, x is a function of t. Now what we have is the entire integral. Everything is written in terms of t. This is an integral dt on the t-axis. This is a Calc 1 integral. And of course we're all really good at computing those. So we went through some examples last time. Here's a parametrized curve where we were thinking of some sort of a density. Describing a distribution of mass or whatever over that curve, and various things you might want to compute you can write down as line integrals, and then it's just plug and chug. The most interesting part of the plug and chug, of course, is rewriting the differential. We compute the stretching factor there, our speed. That stretching factor then goes into there, right? Which likewise there, and there's our integral dt, and off you go, compute. Okay, so that's where we ended it last time. More examples. I'm going to let y'all just read through these examples. They're morally equivalent to different physical quantities that are still written down as line integrals, and the pullback is the same process. Okay, so new example. Now this one is something that's not, we haven't really done anything like this particular example before, so I wanted to go ahead and do this one out. So suppose we have a fence that's made, something like this. Now notice that the height of that fence is not constant. Right, the height of this fence depends on where you are in the yard, and why do we have height as a function of position in this way? Well, I don't know, something to do with the shade that we want to project onto our property, and where are we growing? What kinds of plants that require more shade or less shade? Where's the house? And south-facing windows, stuff like for whatever reason. This is our height of the fence is a function of location. Okay, and the question is, what's the area of the fence? This is one of those rare situations where you can actually see why you'd want to actually know an area. Right? Remember, most of the time, the reason we care about integrals is not because we actually care about area. Most of the time we care about integrals because they represent some physical quantity or another that we're actually interested in. Here, I actually care about area, and you can imagine maybe I want to paint this fence, and I need to know how many square feet or how many square meters or what have you am I going to have to buy paint for? Okay. All right. Okay, so step one, realize that we're talking about a line integral. So over this curve, there's a curve in the plane. Over that curve, I want to do a chop it up, add it up. Specifically on each little piece of that curve, such as that little piece right there, I would like to know what is the height at that location, and then the quantity I'm interested in is that area, which is going to be height times, how big is that little piece of the curve, which is ds. All right, so we're going to be interested in a line integral. Height times ds, because height times ds gives me the area of the little piece. Okay. All right. So knowing that we're doing a line integral, we're going to need to parameterize this curve. Now, good news. This is an easy curve to parameterize. The units that I've chosen here, this is just the unit circle. in the XY plane, easy parameterization. Okay, and then it's kind of all over at this point. It's just plug and chug. To figure out what ds is for an application like this, well, ds is speed times dt, and so I need to take my parameterization, compute the velocity, like so. The speed is the magnitude of that velocity, so, Pythagorean formula, and very conveniently, speed turns out to be 1 in this case. And then it's, again, a standard pullback, plug and chug. ds is speed times dt. There's our speed of 1. Everything else is just plug in. So h is a function of x and y. Well, the parameterization tells us that x is cosine t, y is sine t. That was given in the parameterization right there. Right? This is what x is, and this is what y is. Right, so don't forget, parameterizations tell you how to plug in for the output variables and how to pull those back to be in terms of the input variables. Okay. And now that everything is in terms of t's, it's a Calc 1 integral, and so off you go, plug and chug. Okay. All right. Okay, so we're going to move on now and talk about a new kind of line integral. That's going to sound a little weird. At a glance, this will look like it's just a line integral again. Certainly from the picture, you'll notice that we're going to be doing an integral on a curve in not 1 dimension. So we're going to do an integral on a curve, in this case 2 dimensions, but it's morally equivalent, 3 dimensions. We're going to do a chop it up, add it up. This is starting to feel a lot like the line integrals we've already written down, right? In this case, we're going to look at a different physics application, and it's hard to see this coming in advance, but it's just going to turn out that just because the physics is a little bit different, we're going to end up with a kind of a different mathematical object after we do our chop it up, add it up. So anyway, let's just kind of go through it. We're going to compute work. And flashbacks to chapter 12. Y'all remember work, right? It's one of our first applications of dot products. So y'all all saw the high school formula for work. The high school formula for work is equal to force times distance, and they write it down like this, and then they have to kind of put an asterisk there and say, asterisk, except you've got to look at components. We're only interested in the component of the force that's in the direction that you're actually going, and there's this whole conversation, and trig comes up, and, it's a whole thing. So we modified that in chapter 12. We took advantage of how dot products worked and said, well, in fact, we don't have to have that asterisk. All we have to do is just say, look, if you're going over if you're displacing over a straight line displacement like that, over which you're applying a constant force like that, all of that component issue is completely taken care of by the dot product. So let's view the force appropriately as a vector. Forces are vectors. Forces aren't just magnitudes. Forces have directions. Magnitude and direction. It's a vector. Displacements, likewise, have a direction. Anytime you move a given distance, you move that distance in a certain direction. Right? So these naturally are vectors. Let's treat them as vectors. The dot product totally takes care of the direction asterisk for us. And so we have this revised, much improved formula for work. So if you didn't see high school physics with work, then this is a new experience. But if you did see high school physics, this is an improved formula. Okay, so this formula that we were so happy about in chapter 12 does, however, still have an asterisk on it. And the asterisk, it does assume that this force is constant over the entire displacement. It further assumes that this displacement is over a straight path. So straight line displacement. constant force. So let's address this very real world problem. What if you are not moving over a straight line? What if, a lot of roads around here, for example. What if your path is not straight? This is very physical. It's very realistic. We just don't go in straight lines all the time. What if the force isn't constant, right? It could very well be that the force, maybe when you start is something like that, but then the forces move in these weird ways. So they're not always pointing the same direction. How do you deal with that? Can you just kind of pick one of the force vectors and kind of amalgamate all the displacement vectors and just say, let's just throw it all together and just do it like that? No, of course not. Right? That doesn't make any sense. You couldn't possibly. Okay, so now, no surprise, and I've kind of already given this away, but what we do in this situation, as we do in most applications that we see in this class, is we do a chop it up, add it up. Right? And so the idea is that even though on this curve, the curve is not straight, if I chop it up into little pieces, that little piece there is approximately straight. Not exactly, of course. Yeah. The forces, well, they vary wildly. I mean, that force vector is very different from that force vector. However, if I look on this very small little piece, I just don't move very far, and the force vector there and the force vector, move a little ways over, it's probably pretty close to the same. Okay, so the idea is if we chop it up into little pieces, then on each little piece we're looking approximately at straight lines, approximately with constant forces, and so on each little piece we should be able to use this formula. And then now, our hope, and we're not going to deal with the formalities of this, but the hope is then that as we chop finer and finer, that all of our little approximation round-off errors approach zero. And in the vast majority of situations, again, I don't want to make that precise. Yes, they do. So we're just not going to worry about that in this course. So anyway, here's that breakdown. So again, here's our little piece of curve. Let me do that with where it's more visible here. Here's our little piece of curve. And we've talked about that before as being ds. However, we're not interested particularly at this moment just in how long it is, right? Remember, now we're viewing it as a displacement. We approximate not the length of it, but we approximate the displacement along it with our differential dx. Right? So there's our, on our little chop it up, add it up, looking at one piece at a time, that's our displacement that we're going to dot with our force, which again is approximately constant over the entire piece. And force dot displacement a la chapter 12 gives us the amount of work that we expect that it would take approximately to move along that piece of curve. How we doing? Okay. So, our adding up process, if I want to add up all the little bitty pieces of work, well, each little piece of work, dw, that we just wrote down, dw is f dot dx. And, there we are. There's our formula. Now, so let's talk about what we have here. This is, it's a line integral in the sense that we're doing a chop it up, add it up along a curve. So this is a integral over a curve. Thus, line integral it feels a lot like the line integrals we've done before, but the rest of what we've written down is very different. We do not have here a scalar valued integrand like density, like mass per unit length. That's not what this is. That's not scalar valued. That's a vector valued integrand. It's a vector field. Right? We are not looking at a scalar valued differential. We're viewing our vector position differential as our differential. So there's not a ds scalar or a dx or dv or something like that, all of which are scalars. This is a vector differential. That's weird. That's certainly very different from what we've seen before. Okay. Finally, this is not just a regular old multiplication. That is a dot product. Right? So this is an algebraically significantly different critter. Even though physical quantity that we're thinking of as accumulating over a curve, we're doing a chop it up, add it up, just like we did for all of our physics applications on curves up to now. This physics application, though, the way the physics formulas work, we just end up with a different kind of expression. Okay, so new thing. Now, how do we compute this thing? Here's the good news. We can take approximately the same strategy and still compute the same thing in approximately the same way. So let me remind you what our strategy was. Our strategy was to say, okay, here our curve over which we're doing this, chop it up, add it up, our domain for this integral. Let's view that as being an image. View it as being an image of a new pullback domain between A and B. Let's try to take everything that's written in terms of x's and y's. Let's try to pull back through the parameterization to rewrite it in terms of t's, thus resulting in an integral on the t-axis, again, which we already know how to do. We're happy with single variable integrals. Okay. Here's some more good news. We've already kind of set all this up, right? We already know, let me zoom in here for effect. We already know that when you chop up this little piece of the curve there, we've already given a name to the vector representing the linear approximation of displacement along that curve. We've called that dx, and we already have a formula for it. It's v dt. Now, when we were doing the other kind of line integrals, scalar integrands, scalar differentials, we went further and said, and the thing we care about is ds, which is the magnitude of this thing. Well, we don't have to do that here. Look back at what we're actually interested in. What we're interested in is, it says so right there, dx. I don't need to take the magnitude of it to find ds. Dx is what I want. So the counterintuitive thing about this is that when you're computing one of these brand newfangled kinds of integrals, such as this, this line integral of a vector field with a vector valued integrand and a vector differential, this more sophisticated thing, oh my gosh, it's the first time we've had a dot product inside of our integral. It's actually easier to compute than scalar line integrals, because you don't have to take the magnitude of stuff. I don't need to take the magnitude of the velocity to get speed, or equivalently, I don't have to take the magnitude of the dx vector to get the ds vector. I just have the dx vector. Dx is v dt. It's a vector. Leave it like a vector. And then notice, of course, your vector field f is a function of position. Position's a function of time. And so you have here vector dot vector, which is no problem. Just dot it on out. Okay. All right. So again, that's one of the counterintuitive things. When you're doing a line integral of a vector field, they're a little easier to compute than scalar line integrals or line integrals of scalar valued functions. Okay. Alrighty, so let's compute one. Okay, so here's a very real world physical scenario. So you're walking along some path, and as you walk, wind is blowing and wind is exerting a force on you. Right? So here's the force that the wind is exerting on you. Note the choice of words. Wind is exerting a force on you. Okay. All right. So we have a force, and we are walking along counterclockwise along the top half of the unit circle. Let's draw a picture of that so we see what we're doing physically, geometrically. There's the unit circle. We're going counterclockwise along the unit circle. Like that. And so moving along this curve, like so, with this force applying to us, how would I compute the total amount of work? Well, now again, very importantly, we cannot just say, we start here and end here, and therefore there's our displacement. Not at all, right? We are not just moving straight along the x-axis. We are moving along this curve. The way the wind is blowing over here is significantly different from the way the wind is blowing on the x-axis. So you can't just say, I'm just going to sort of combine my entire displacement into one great big step. No fair. Right. Okay, so it can't do that. So we've got this curve domain, and we've got a vector field for the force, and off we go. Now, here's a subtlety of physics I have to mention. I don't want this to turn into a physics class. Despite my background, and on a certain level, I kind of want it to turn into a physics class. But as a mathematician, I don't want this to turn into a physics class. But you do have to worry about opposing forces. Okay, so for example, let's look at this pen here. Right, just a quick digression. This pen, there are two forces acting on the pen. Gravity is obviously one of them. We're all everything's subject to gravity. Gravity is pulling down on this pen. That's what gravity does. Right? And yet, the pen does not accelerate. Well, that's because I am applying another force, right? My hand is applying a force upward. There are two equal and opposite forces applying to this pen. They're like this, right? Notice that because they add up to zero, because the pen's not accelerating, because they add up to zero, these two forces are negatives of each other. That's just a little quick physics aside. So when you describe the force relevant in a given situation, you have to ask yourself, wait a minute, which of these two forces are we talking about? Are we talking about the force that I am applying to oppose the gravity, or are we talking about the force that the gravity is applying that I have to oppose? Which one are we talking about, and which one am I actually interested in? Right? So here in this situation, we want to compute how much work do you exert. If I want to know how much work I exert, I need to talk about the force that I am exerting. Notice that's not what was given. What was given is the force that the wind exerts on me. Right, so the wind may be pushing me back that way. I have to push the opposite to oppose it. Okay, so heads up. You got to think about the language. How is the question phrased? You can't just take whatever vector field is given to you and say, it's a vector field. That's the integrand, right? You got to think about, wait a minute, what is this? Which way is this the this way, or is it the that way? Which one am I given? Which one do I actually care about? And are they the same? Or are they the opposites? So in this case, this is the opposite. So I push with a force of negative F. That's the force I push with. As I displace myself along this curve in little increments of dx, yeah.
Why wouldn't that mean you just stayed in place if you were pushing with a negative the same force?
Yeah, no, that's a good question. So I guess I'm pushing with an ever so slightly greater force. So we're going to ignore, we're not going to consider stuff like, I'm going to apply significant force. I'm going to gun it in my car and, do a kind of half a donut as I go around this thing, right? I just want to consider sort of slowly moving along. So we're going to ignore stuff like, the actual accelerate, starting from zero, the small acceleration that I'm going to make as I go around. And I'm going to ignore the fact that I have to hit the brakes, before I get to the end, so I don't go flying past my endpoint, and just consider sort of just the bare minimum work there. Yeah. Right. Great question. Thank you. Okay, so there's my expression, and now that we've got it written down as physics, now it's really very plug and chug. I just parameterize the curve. Well, here's our unit sphere again, so the parameterization is easy to do. That parameterization, that's our good old, plain old parameterization of a unit sphere, cosine and sine. Okay. Quick observation, do be careful. Think about the range of values of t. I start here where t is 0, right? And I end here where t is pi. Those are the values of t, anyway, that you plug into this parameterization to get those points on that path. Okay. All right. So, got our parameterization, and it's all over but the algebra. Given x, take the derivative to get the velocity v. Dx is v dt. No magnitudes. It's just v dt as vectors. Okay. Negative f. So there's the minus sign. Right? That minus sign there. Here it is. Don't inadvertently drop that. Okay. The force F was given as y comma negative x. So F is y comma negative x. Now don't forget a little detail here, but don't forget that x is cosine t and y is sine t. Right, and you plug all that in, you get this. Do the dot product. Lucky break. Pythagorean identity. Oh, how nice. I happen to get one. You're not always going to get that lucky, of course. But the point is, it's all single variable calculus from here. Yeah.
So where did the negative sign go?
Oh, yeah. I mean, here it is. So this minus sign, let's look at one component at a time now. My first component is negative y, which is that. Yeah. And then my second component is, let's see, negative of negative. So my second component is actually positive x, which is there. Yep. By the way, this is a good example of why I suggest, don't try to do too much in your head, especially when it comes to minus signs, right? So we have the negative of the force, and the force has a negative in it, and what if, even worse, what if the parameterization might have had a minus sign in there somewhere, and there's just, oh my gosh, it's so easy to inadvertently miscount your number of minus signs. So I'm a big believer in write it down explicitly, and don't try to sort of skip steps algebraically in your head. Yeah.
Since it's a dot product, is it okay for us to move the sign outside like the integral?
Yeah, sure, right. Yeah, absolutely. No problem. Okay, now here's a variation. You might have noticed that in these previous examples, I've been giving myself the very familiar parameterization, counterclockwise unit circle, right? Okay, so that's an easy one. So let's talk about a not the same situation. What if I'm going clockwise? How does that change things? So what if I am going like this, for example? Well, you can't just say cosine t sine t. Cosine t sine t moves counterclockwise, right? You can tell because you can compute the velocity vector, and the velocity vector is that way, right? I mean, this is not a throwaway point. So if you're talking about work and forces and vector line integrals, the direction matters. Now, with mass, it doesn't. If you're computing a scalar line integral of mass, the mass distributed over some wire, if you add in that direction or if you add in that direction, who cares? What? It's the same mass. You're just adding, right? Addition's commutative, right? No problem. With vector line integrals, it really does matter because there's a very different phenomenon of me lifting a pen versus lowering a pen. Right? One of them's a positive. It takes me a positive amount of work to lift up. It's actually a negative amount of work for me to go down. By the way, this is a weird concept, right? Negative work. It's hard to relate to. Personally, I've never gone out and done a day's work and felt like, yeah, I've done a negative amount of work, right? Sadly, we're not built that way. But since I started teaching this material long ago, a new technology has come up that's allowed me to, I think, very effectively talk about and communicate the idea of negative work and to make this totally plausible and reasonable. Hybrid cars, right, have something called electronic braking, or it probably gets called different things. But when you drive a hybrid car up a hill, right, the battery is running. You're losing battery charge as you go up. When you then turn around and come back down the hill, well, you don't want to fly down the hill. So what do? You apply the brakes. The brakes don't work the same way that they work. Old cars, brakes are just two pieces of stuff that cram together and create friction, and that slows it down by generating a massive amount of heat that just disappears, and that's energy that we never could take advantage of ever again, right? Electronic braking is some really sophisticated, cool stuff that uses very smart engineering involving magnets and E&M, coiled wires and stuff. The math behind how electronic braking works is stuff that we are going to cover in this class. But later on, we don't quite have the tools for that just yet. But back to the hybrid car, going down the hill, you apply the brakes in one of these cars, and what it does is it decelerates the car in such a way that it's not turning the kinetic energy into heat that's never seen again. It disappears into the atmosphere, right? It's turning the kinetic energy of the car into battery energy. Right? So you charge your battery by driving downhill. Pretty wild. So there you have a pretty relatable idea of negative work. The car does a negative amount of work in going down the hill, as is reflected by the fact that the battery, in going down the hill, the battery loses a negative amount of energy. It gains energy. Right? Charge the battery. Okay. Anyway, I think that's pretty neato. A little digression, but okay. So let's talk about if we're going clockwise here, right? How are we going to compute the amount of work that takes to do it? Well, I'm going to show you a couple of different ways to parameterize this curve. Here's here's a really good way to do it. Let's call this the first way to do it, and that is let's define this angle here to be t. Now that's different than what we've ever done in the past. In the past, we've always defined, t is basically theta. Theta is from polar coordinates. Polar coordinates is nice because we've already memorized those formulas, right? Okay, that's not what this is. We're making a different choice of t. Notice that with this choice of t, we start here where that angle t as defined there is 0. I'm not talking about theta. Right? T, as I've defined it in that picture, that t is 0. And this point over here, where we end, after going along like that, by this definition I have of t, this point here is t equals pi. And so you can see, with this definition of t, we are going clockwise along this path. With t going from 0 to pi. Okay, so I can define anything I want, but how do I get x and y in terms of this t? The nice trick for that is to make the observation that, okay, well, if this angle here is t, then that angle is pi minus t, and the good thing about that angle is it's my good old polar theta. And so with theta having been identified as pi minus t, I can write down x and y. X and y are cosine of theta, sine of theta. Theta, look at the picture, it's pi minus t. Everybody on board? And then it's just a matter of remembering all of your trig symmetries. By the way, I'm aware of the fact that a lot of students are very rusty on their trig. It was a long time ago, right? And I know. But the world's full of circles. And so trig doesn't go away, especially for those of you who are engineers. And this is an engineering application we're seeing here. So it's going to be assumed in this course on my midterm exams and also on the final exam. It's going to be assumed that you are proficient and, fully up to date and, ready to go with all of your, basic trig. So trig symmetries, for example, are what these are. And don't forget also you have a bunch of trig identities and stuff like that, yeah.
So of the trig identities, do you think, which ones are
Yeah, I can't make an exhaustive list. I'm going to say that most of them. Let me not make an exhaustive list because I don't think I can enumerate it. But it's going to be approximately a trig syllabus. Yeah, right. Okay, so remembering all of your trig, the point is then position as a function of time. There you go. This is a parameterization that goes clockwise. Now, let me show you a different way that you can get to the same answer. Perfectly valid way of getting to the same answer. And that would be to start with a different curve. Let's start with the curve that starts here and goes around like that. Right? So this curve here, our good old counterclockwise, that is what I'm going to call cosine t, sine t, right? Our old friend. And then let's make the observation that this curve that starts on the right and goes counterclockwise, and this curve that starts on the left and goes clockwise, these two curves are reflections of each other over the y-axis. And the way you reflect over the y-axis is you stick a minus sign on the x-coordinate. Right? So you can view this as that we're starting with this green parameterized curve down there, and that by the reflection we put a minus sign specifically on the x-coordinate because of the reflection. So alternative, different point of view. Some situations one of these ideas might be more convenient than the other, or vice versa. Okay. All right. Okay. All right. Now let me give you a third way to solve this problem. This is a math argument, okay? But let's not forget that when we write down these integrals, we're talking about Riemann sums. I remember I'm a big believer in this point. So integrals are Riemann sums. We are, in fact, adding up a bunch of terms along a bunch of little pieces of curve, right? And addition really is commutative. Right? So we're adding up all these little pieces of curve. On each little piece of curve, we get various terms. The force that I write down, at that some point on this little piece of curve, it's the same force vector, no matter which way I'm going. There's only one thing that changes when you're going different directions. On the one hand, you're going one way, and on the other, you're going the other way. And the only difference between these two different directions is a minus sign. So thinking about this from the point of view of Riemann sums, going one way around the curve as opposed to another way around the curve, you're adding up pretty much all the same terms. Everything's the same in all the terms, except every single one of the terms has a minus sign in one of them as opposed to the other. So if the terms are all negatives of each other, then the integrals are negatives of each other. So this is a really nice observation. But when you're a vector line integral going two different directions along the same curve will always be negatives of each other. That's fine. Everybody happy with that? In fact, this is a nice rule to remember. Okay. Importantly, it's got to be the same curve, same exact set of points. Okay. All right. Now, let me give you a third option that you're not allowed to make. Third argument that you're not allowed to make. Students do this sometimes, and I'm very uncomfortable with it. A lot of students would like to come back here to the original picture and say, okay, well, walking counterclockwise. I know how to parameterize counterclockwise. I'm going to write this down, and the way that I'm going to communicate that we're going clockwise, right? The way I'm going to sort of change the direction is I'm going to say that we are going to start at t equals pi, and then we're going to end at t equals 0. And just in the resulting integral that I write down, I'm just going to say integral as t goes from pi to 0. All right. Now, first, the good news. This will give you the correct answer numerically. Right? And the reason it gives you the correct answer numerically is because, as y'all all know, as y'all all remember from Calc 1 class, if you have an integral and if you do this to the bounds, well, the whole f of b minus f of a becomes, well, you might call it f of a minus f of b. You clearly get the exact negative in terms of how you compute it. Right? And so, yes, numerically you will get the correct answer. Reminder, this class is not about answers. Right? This class is about arguments that make sense. Right? So let's talk about, to what extent does this actually make sense? The student or the speaker, whoever's making this case, that clockwise is just counterclockwise where time goes backwards. This is really fishy. Right? I am extremely uncomfortable making the case for how physics works when time goes backwards. I don't think you guys should be comfortable with this idea. Here, let me make a physics argument that time shall flow backwards in my argument. This is not good. Right? Does everybody see the problem then? Okay, so this is not okay. Again, numerically, yeah, they'll get the right answer numerically. But this is not acceptable reasoning until you can persuade me that you are, irrefutably knowledgeable on the nature of backwards moving time, which you can't do, right? So anyway, don't make this argument, please. It won't get credit. This is not a valid line of reasoning. And asterisk, coincidentally, you'll get the right answer at the bottom of the page that I don't care about. Does that make sense to everybody? All right. Okay, moving along. So we've done a bunch of applications. We've done a few applications of line integrals. Let's go back to it. Our first discussion, we were talking about work. We started off with this question of work, and we motivated this construction computed by this formula from the point of view of this specific one physical application, work, in which the integrand always has the same interpretation. This vector field integrand here represents forces. Right? So what we've got is then, we've got a mathematical construction that was motivated from a certain point of view on vector fields, thinking of vector fields as forces. Okay. Now that we have this mathematical construction, we can reasonably ask the question, hey, suppose, and let's just say, suppose that I were interested in a vector field that doesn't represent forces. What if I were interested in a vector field that represents the flow of a fluid, right? I mean, this is we have these two big interpretations of vector fields. One is forces, the other is flows of fluids. They're pretty different physical scenarios. If this were the other physical scenario, now representing the flow of a fluid, question, what does this represent? What does that mean? Well, it's not work, right? Work is what you get when you think of this as a force, right? You get work if this is a force, because work is force dot displacement. If this is a fluid flow, this is a different thing. So this is a pretty non-trivial question. Suppose your vector field represents a fluid flow. What is this vector line integral that we've just written down? A quick calculation. A reminder, we have this picture. There's our little piece of curve. We've talked about the dx vector. Colors. Come here, colors. We talked about the dx vector, that little bitty thing. We've also been making extensive use of our velocity vector. Velocity is x prime. It's the derivative of position, right? That's convenient. Don't forget, we also have a third vector in this mix. We have this thing called t, our unit tangent vector. Right? And this is going to end up being a convenient object to play with in this context, as it turns out. So here's the little game I want to play. Our formula for our dx vector, right? This is how we compute vector line integrals so far. Make the observation that velocity is a direction and a magnitude. T is the direction. It's the unit vector direction. Little v is the magnitude. It's the speed. Right? So this is just a fancy way of saying the velocity vector. And then I'm going to take these parentheses. I'm going to move the parentheses around a little bit like so. And then recall that this thing, v dt, is ds. Right, so all together then, notice we have an alternative way to think of the dx vector. Instead of thinking of the dx vector as velocity dt, let's think of it as unit tangent vector ds. And in so doing, right, with this formula for dx, again, let's move the parentheses around a little bit, and I can think of this integral that I'm, keep in mind, we're looking at these vector line integrals. I can think of that vector line integral as that, namely this. All right, so flashback to another application of dot product from a long time ago. Dot product with a unit vector gives you a component. All right, now we're just kind of moving symbols around at this point. Right, it's not clear what this has to do with fluids, other than we're moving things around. Before we get to fluids, let me make one quick observation, and that is that now notice that our new algebraic object, our vector line integral with a vector differential, now looks like a scalar line integral. Well, that's familiar, right? It's tempting to say, "Oh, it really is. Oh, it's good news. This is just like scalar line integrals, like we saw in previous lectures." Beware of this. That's still not true. It is still the case. I mean, this is just sort of sweeping the dirt under the rug. It is still the case that what we are adding up here, our integrand, if you will, still depends very significantly on the piece of curve, right? So we're looking at a component in a direction. That direction t is the direction that the curve is moving. So we kind of just shuffled things around. In my opinion, this t vector is still part of the differential, really, because it's part of what you get from looking at the piece of curve. Okay, so this is a scalar, but it is not a scalar function of position. It is not like density. This isn't. It has certain features in common, but very importantly, this is different from a density. So don't make the mistake of thinking, vector line integrals are just like scalar line integrals. They're really not. Okay. All right. So what does this have to do with fluids? Bad news, good news. Here's the bad news. This object here is not, I'll say what maybe we were kind of hoping for. This is not a perfect mathematical representation of a physical quantity that we've already got an idea of. Right? Wouldn't it have been nice if this was, volume or something, some pre-existing thing that we already know, that we already have some sense of. So we didn't prove anything here like, good news, this is, with forces, line integrals are work, and with fluids, line integrals are, something that would have been a satisfying ending. That's the bad news. Here's the good news. Even though this is not a pre-existing concept, I can point to this thing and say, hey, this is a concept that I know how to compute at this point, and let's ask ourselves, is this something I can make some sense out of in the context of fluids? And the answer is yeah, absolutely. This thing that I'm looking at here says how much is the fluid flowing along the curve, right? The F represents the fluid flow, T represents along the curve. So this component says to what extent is the fluid flowing along the curve at a particular spot on the curve, and adding that up over the entire curve gives you this idea. This expression, what is a line integral? It's a way of measuring how much the fluid in total is flowing along the entire curve. So this is kind of a new physical object to pay attention to. Now, you might complain, we're making stuff up at this point. Just because we algebraically ran into something doesn't mean that this is a physical concept that we're going to need, and that's true. But good news, this actually ends up being a physical concept that you're going to need. Those of you who are engineers, if you end up taking fluid dynamics classes, this is an important thing that will come up. So anyway, I just wanted to give a little discussion about how to think of fluids in that context. Okay, one last little quickie, and then we'll call it a day. Do be on the lookout for every so often you'll get lucky geometrically. So suppose you want to compute this vector line integral. Your curve is some path moving along the surface of the unit sphere, let's just say. Like, so maybe you're taking a cruise on a boat on the surface of the Earth, right? And let's suppose that your force is like this. Okay, so you've got a curve, you've got a force. Let's compute the amount of work. Plug and chug, right? You can parameterize. Phi and theta are functions of time. Rho is a constant. You're on the sphere. You write that out in spherical coordinates, get position as a function of time, take a dot product. You get this great big, huge, nasty monster of a formula if you brute force this. The neat observation to make is that because the curve is moving along the surface, dx is always tangent to the sphere, whereas the force, look at that, the force is always a multiple of position, and the way spheres work, that means it's always perpendicular to the sphere. So what we have here is in fact a dot product that's always zero. This dot product, dx dot f, always zero. We're adding up a bunch of zeros. This integral is zero. So heads up, every so often you do get lucky. It's more common than you might think. Again, just quick, remember I had a second major in physics. I went through a lot of physics calculations involving integrals, and this is a very common scenario. This kind of thing where you're interested in a line integral, and it just turns out you're adding up a bunch of dot products that are all zero. So anyway, heads up for this kind of thing. We'll call it a day there. See y'all later. Have a good one.